In section 3.4, as you can see, we're going to be looking at invertibility and isomorphic vector spaces. You may be familiar with these words. In fact, you may be familiar with these concepts. If you've invertibility we've seen since high school, even though it was in an informal way, probably. And isomorphic, maybe you've seen this in an abstract algebra course. But this is a pretty lengthy section, so let's not waste too much time. So first off, we'll introduce a definition of invertible. So a linear map T is called invertible if there's another linear map S such that S composed of T, or ST, equals the identity map on V, and TS equals the identity map on W. So a linear map S satisfying ST equals the identity map and TS equaling the identity map is called an inverse of T. Right? So a high school example I'm going to show we're just going to show that the inverse of a linear map is unique. And just like any unique proof, we suppose there's two and show that it's actually the same one. But before I do move on, just to say a bit about the definition. So T, let's say, maps V to W, and S maps W to V. To V. So these are inverse if for an element X, we'll call this one Y, and then we get the element Y and move it, and it maps back to X. That's the identity mapping. So in that case, ST is equal to identity map, and TS can be thought of the same way, just like a reverse order, and that's how we get the identity map, and that's what we call inverses. They're inverse of each other. And as you've probably seen in high school, when you take inverses of the composition of two functions, and you plug in x and it gives you back x for the composition of those two functions, then those are inverses. But I'm going to go over that right now. First, we're going to prove that a linear map has a unique inverse. So short proof, suppose T maps is a linear map from V to W, and that it's invertible, and S1 and S2 are both inverses of T. Well, then S is just equal to S1 times the identity, right? That composition. And the identity, we can write it as T composed of S2, right? So that composition. Why can we write it like that? Well, because S2 is an inverse of T, right? So they should be equal to the identity mapping. Now we can use the associative property. Because S1 is also an inverse of T, it equals I. So I and S2 are just equal to S2, as the identity mapping doesn't change anything. Therefore, S1 equals S2, showing that their two different inverses are in fact the same one, not different ones. So S1 thus equals S2. So again, linear maps have a unique inverse. So just as notation, this shouldn't be anything new. Again, since high school, we've seen this. We denote the inverse with a superscript of -1, right? So the inverse of T is just T with the superscript -1. As you can see here, the composition gives us the identity mapping. And here's a high school example. Remember when you were asked to show that this function f has an inverse? Well, remember that to see if a function had an inverse, we would check something like something called a horizontal or vertical line test. Right, we would do the vertical line test. If it crossed at 2 points, then it did not have an inverse. This is a bit of foreshadowing to what we're going to see right now. Now, again, in high school, it was very informal. They put it in a easy version so we can understand, but they do have to spare formalities, the rigor. So we're going to see what we actually were doing back in high school. So again, this is just an example. You can pause it if you need a little reminder of what you did in high school. But we're going to be working with inverses here. So we get the following theorem. A linear map is invertible if and only if it is injective and surjective. So a linear map is invertible if and only if it is bijective, so to speak. Proof isn't complicated, but it is biconditional, so we will have to prove two directions. And I know this looks really long, but believe me, it's pretty straightforward. So let's go line by line. First direction, we're going to suppose that T is a linear map from V to W. So we're going to first suppose that T is invertible, right? And because it's invertible, we're going to show that it is injective and surjective. So first, to show T is injective, suppose U and V are in our vector space V, and TU is equal to TV, right? To show injectivity, we're going to have to show that this implies that U is equal to V. So U is equal to the inverse of T composed of TU, which is the same thing as the inverse of T composed of TV, which is equal to V, which shows us what? Well, that U is equal to V. And again, this here is the identity mapping, so it really doesn't affect U. It affected it and just, actually it doesn't affect it, but it lets us show that indeed U is equal to W. I'm sorry, to V. So that shows injectivity. So again, still assuming that T is invertible, we want to show that T is now surjective. So let W be in big W in our codomain. Well then W, again, is equal to this because this is the identity mapping, so it does nothing to W. But what does this show? This shows that W is in the range of T. Why? Well, because this here, it's we're mapping, right? So W is the image, right? T of some element, right? We don't know specifically what element, but we know it is the image of an element in V. So W is in the range of T. Therefore, the range of T is equal to W. Now to prove the other direction, suppose T is injective and surjective, and now we want to prove that T is invertible. So for each W in W, we're going to define S of W, as it shows here, to be the unique element of V such that T composed of SW is equal to W. And because we're assuming T is injective and surjective, we get that this element is unique, right, as it says here. So what is this saying? Well, it's always useful to draw pictures, right? So let's go step by step. Let me erase here. For each W in W, define S sub W. So S sub W maps W to V. The unique element of V such that T of that element is equal to W. So then this maps it to that element, and this is T. That's what that line's saying. So clearly, T composed of S equals the identity map on W, right? Just as we define this, well, clearly we get the map back to W. So we get the identity map. But what about S of T, right? So to prove S of T equals the identity map on V, let V be in V, and I'm going to erase this picture just so it doesn't obstruct. Well then, T of S of T of V, what is that equal to? Well, using distributive properties, that's just equal to T of S of T of V. We know these two are what? Inverses of each other, right? So that's the identity mapping here. Identity times TV, or of TV, is just equal to TV, right? So the equation implies that S of T of V is just equal to V. And again, that's because of the fact that T is injective, and we get that S of T thus equals the identity map on V. But wait a minute, doesn't that conclude the proof? Well, not necessarily. We still need to show something about S. What we need to show is that S is indeed linear. So suppose W1 and W2 are in W, then T of SW1 plus SW2 is equal to T of SW1 plus T of SW2, which again, they're inverses, so W1 plus, we get W1 plus W2. Right, so this satisfies the additive property required for linearity. Give me a second. By the definition of S, this implies that. Oh, right. We're saying the same thing. Right, so we're satisfying the additive property of linearity. Now, what about the scalar multiplication? Or in other words, homogeneity. So if W is in W and lambda is a scalar in F, then T of lambda times S of W, well, that's just equal to lambda times T of S of W, which is just equal to, again, because this maps to identity, that's just equal to W, so lambda W. Therefore, lambda S of W is the unique element of V that T maps to lambda W, right? Therefore, we get the homogeneity, and therefore S is linear. So again, not too complicated. I don't want to say easy, that's not a useful word, but it shouldn't be too difficult to see each step by step. And again, pictures always help. So wherever you need one, try to draw one yourself and see how things are working out between the maps. Okay, next definition, the second topic we're going to be looking at are isomorphisms. So an isomorphism is an invertible linear map. That's all an isomorphism is. So two vector spaces are called isomorphic if there's an isomorphism from one vector to the other. Another way a lot of professors teach isomorphism just as an intuitive way is two sets. There's an isomorphism between two sets. In this case, I'm talking sets, not maps. If they're really the same set, just with different names. So for example, I should have a picture. Let me just read this theorem first. Two finite dimensional vector spaces over F are isomorphic if and only if they have the same dimension. I should have the picture. There we go. So these are in no way linear maps. This is from graph theory actually, but it's a really useful picture to help us with our intuition. So these two graphs are actually isomorphic. Graph G and graph H are actually isomorphic. Why is that? Well, because you can, without breaking off any edges, you can convert this graph into this one or this one into this one. They have the same number of edges, they have the same number of vertices. And if we just rename them, they really just become the same graph. So if we rename A as 1, as it shows over here, B as 6, C as 8, D as 3, so on and so forth, we really get just the same graph. That's what an isomorphism is. So as you can probably imagine with linear maps, with vector spaces, two vector spaces should be isomorphic if and only if they have the same dimension. Now that may be intuitively clear, right? But the proof may not be, although again, pretty straightforward. And before we do move on to it, I just want to mention isos and morph. So isos in Greek actually means equal, and morph means shape. So isomorphism is really just saying equal shape. And then last thing I want to point out before we move on, isomorphism is an invertible linear map. So those two things can just be, if you say something is an invertible linear map, then you're just saying it's an isomorphism or vice versa. Okay, so again, biconditional proof. Suppose V and W are isomorphic finite dimensional vector spaces. We're going to show that they have the same dimension. So there exists an isomorphism between isomorphism T from V onto W. Because T is invertible, we have that null of T is equal to 0. Why is this the case? Well, because we saw that if T is invertible, then it's injective. This property here comes from injectivity, as we saw in previous lectures. And it also is surjective, so range of T must equal W. Therefore, the dimension of the null space of T is 0, and the dimension of the dimension of the range of T is the dimension of W. So this formula, what formula is that from? Well, that's from the fundamental theorem of linear maps, right? So this equation, dimension of V becomes dimension of the null space of T plus the dimension of the range of T, which is just equal to dimension of V is equal to dimension of W, which gives us exactly what we wanted, right? W and V and W have the same dimension. So that proved one direction. Now to prove the other direction, showing that two vector spaces, if they have the same dimension, then they're invertible. Sorry, not invertible. They have an invertible linear map, or in other words, are isomorphic. we need to follow the following steps. So to prove this direction, suppose V and W are finite dimensional vector spaces with the same dimension. We're going to let V1, Vn be a basis of V, and W1 to Wn be a basis of W. Again, same subscripts because we're assuming they have the same dimension. So let T be a linear map from V to W. And we're just going to define the linear map to map this here. T maps this linear combination to this linear combination from V to W. And we get that T is well defined again because these vectors are a basis of V. And T is surjective, well, because this is a basis, right? So it must span W. Also, the null space of T is equal to 0 because, well, bases are linearly independent. So W1 to Wn is linearly independent. Therefore, T is injective. So since T is injective and surjective, what do we get? Well, that it's an isomorphism, right? From the last theorem from the last slide. Therefore, V and W are isomorphic. And we just proved our theorem. Now you may be wondering, this is Fn. So because every finite dimensional vector space is isomorphic to some Fn, why not just study those Fn's instead of general vector spaces? And the reason for that is that if we just really focus on Fn, on those spaces, those would actually lead to other vector spaces. So to explain that, just basically, I'd want to say that if we only study this would really just add complexity and no really new insight to other things that we will pretty soon see in other classes as well. So keep that in mind. Keep that question in mind. And after several lectures, you'll be able to see why. Now, there's an important theorem, quite useful one. Suppose V1 to Vn is a basis of V and W1 to Wm is a basis of W. Well then M, this script M here, remember is a matrix. M is an isomorphism between L, a set of all linear maps from V to W, and all the matrices of the form of with dimensions M by N. So remember last lecture we were looking at matrices. We learned how to convert linear maps, right? T and those T linear map from V to W into a matrix of T, right? So it shouldn't really come as a surprise that there is an isomorphism, but it is quite interesting. So let's go ahead and prove that. And luckily this proof isn't too long. Again, should be pretty straightforward, but it is always good to verify, maybe draw pictures where necessary. So to prove isomorphism, what can we do? We can show that the mapping is injective and surjective, right? We would also need to show that the matrix is M is linear, but we had already did that. We did that last lecture, right? Matrices are indeed linear. So, like I said, we need to prove that M is injective and surjective. So, for injectivity, If T is a linear map from V to W, and the matrix of T is 0, well then T of Vk is equal to 0 for all k 1 through n. And because V1 to Vn is a basis of V, this implies that T is 0. Right? So what does that show? That's showing just injectivity. And to show surjective, suppose A is a matrix with dimensions m by n. Let T be a linear map from V to W such that TV is equal to the sum of all this. I'm not going to explain it. We know this from my last slide, last lecture of matrices, right? That's how we define the linear map T VK, where K is a column, is a sum with all these scalar components of the matrix and vectors of the basis of W, their sum. Well, then MT is equal to A, and that really just comes from the definition as we had seen from the last lecture. So if you haven't seen the last lecture, it's really important to understand what's going on here. And once you do, it should be, again, straightforward and not too hard to see what's going on. But MT then equals A. So the range of M equals all the matrices M, N, right? M by N, as we desired. So it is now surjective. And that's it. That concludes the proof. So from last slide, if you remember all matrices, Fm, the dimension of Fmn was equal to what? Well, just m times n, right? Well, if this here is isomorphic, I'm just going to put it isomorphic to all linear map from V to W, what does that mean? Well, using previous theorems, we can now make the claim that if V and W are finite dimensional vector spaces, then L, the set of all linear maps from V to W, is finite dimensional, and the dimension of that is equal to dimension of W times dimension of V. Right, so this theorem here, along with showing that Fm, the dimension of this is Mn, we can show this result down here. And I'm not including a proof because, well, it's just pretty much using, because of this theorem and this other theorem, this holds true. So that's really neat, right? The dimension of this here is dimension of V times dimension of W. Okay, now we're going to move on to linear maps, thought of as matrix multiplication. So we had previously defined the matrix of a linear map. Now we're going to define the matrix of a vector, which might not be new if you've taken a matrix algebra. So suppose V is in vector space V, and V1 to Vn is a basis of V. The matrix of V with respect to its basis in the n is the n by 1 matrix MV C1 to Cn, where C1 to Cn are scalars, such that V is equal to that linear combination there. So make sure you read this definition. It's probably more confusing. It sounds more confusing than it actually is. but it's necessary to define it like this to, define things formally and rigorously. So an example, matrix of 2 minus 7x plus 5x to the third with respect to the standard basis of P3, P sub 3 of R is, remember a standard basis? So standard basis of this is just, remember, 1x, x squared, x to the third. That's a standard basis, right? So the matrix is just 2, right? Because there are 2 of these, negative 7 of 7 x's. How many x squares? 0. And x to the third, there's 5 of those. So this matrix, I have it horizontally, but it is over here. That's how we get that matrix. So that's the matrix of a vector. So now we get a pretty interesting theorem. It says, suppose T is a linear map from V to W, and V1 to Vn is a basis of V, W1 to Wn is a basis of W, and let K be between 1 and N. Then the kth column of matrix MT, which again, if you recall, we denote it like this, just equals M of V K, V sub K. And if you just read it and really just kind of internalize what it's saying, actually just understand it, you should know that this is what? This just really comes from definition. Remember from last lecture, sorry, how we defined the kth column of MT? It really was just a linear combination. So the proof really just follows from definitions. Also, okay, this one may require, actually, yes, this one we will show. This is not just by definition. Here, suppose T is a linear map from V to W, and V isn't V. Suppose we have the basis of V and basis of W. Well, then the matrix of TV is the same thing, or equal to the product of the matrix of T times the matrix of V. Now, this is quite interesting. So here, suppose V is equal to C1 times V1. So V is just a linear combination of the basis of V, where C1 to Cn are scalars. Well, then TV is equal to C1 times TV1 plus so on and so forth. Well, therefore, the matrix of TV is equal to CV. This here, I shouldn't even read this out loud. I should say though, this first inequality, equality comes from where? How do we know that this is actually equal to this? Well, we are really just using this equation and the fact that M, script M, is linear. That's all we're doing for that equality. Well, then C1, we get this equality that's equal to this. And where did that come from? The second equality comes from this theorem up here, right? So M of VK, that matrix, is the same thing as this over here. So we're really just applying that theorem, which is equal to M of T times M of V. And how do we know that's true? Well, we know that's true because of our theorem from last lecture. I believe it was the last one. It was the linear combination of columns, right? So if we had AC, that was equal to C1 times A dot 1 plus dot 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 CN A dot N. So that's how we went from this to here. And we get that our theorem is proved. So this, you may be having slightly some trouble if you're not too comfortable with matrices. Again, like I said, watch last lecture. Make sure you're comfortable with that material to understand this material. But we're kind of going to leave this, well, not, I shouldn't say leave this behind. But now we go to something extremely important, which I'm actually going to decorate because of how much we mention it. So linear maps from a vector space to itself, right? Most of the time we do from V to W. Well, from V to V, from a vector space, a linear map from a vector space to itself are so important that they get a special name. They are called operators. So a linear map from a vector space to itself is called an operator. And really the deepest and most important parts of linear algebra, as well as the rest of these lectures, the book, deal with operators. Okay, so this is actually the last slide. I know it's been a lengthy lecture, but it's really just an introduction to operators. And again, it's just a linear map from a vector space to itself. And well, a linear map we know is invertible if and only if it is injective and surjective. But for an operator, maybe one of them, just having one of them suffices. Maybe injectivity alone, or maybe surjectivity. Enough is like just having one of those, maybe that suffices to imply that it is invertible. On infinite dimensional vector spaces, neither condition alone implies invertibility. But on finite dimensional vector spaces, we do get the following theorem. Suppose V is finite dimensional and T is a linear map from V to itself. In other words, it is an operator. Then the following are equivalent. T is invertible, T is injective, and T is surjective. Lengthy proof, not really. Definitely not the most difficult to understand in this lecture. I think that was the previous theorem we went over. This is pretty straightforward. I say that for all of them, but I mean it for this one. So A implies B, right? Definitely if one is invertible, we saw that if T is invertible, then it's injective and surjective. So we get A implies B for free. If it's invertible, then it's injective. So that's clear. Now, suppose B holds. Suppose T is injective. If T is injective, then the null space of T is 0. And from the fundamental theorem of linear maps, we get that dimension of range of T is equal to dimension of V minus dimension of the null space of T, which is just equal to the dimension of V. What does that tell us? That the range of T is equal to V. Therefore, it is surjective. Therefore, B implies C. Now, finally, suppose C holds so that T is surjective. We're going to prove that it is invertible. So, if it's surjective, then range of T is equal to V. Again, from the fundamental theorem of linear maps, we have that the dimension of the null space of T is equal to the dimension of V minus dimension of range of T. And well, it's basically saying dimension of V minus dimension of V, which is 0. Therefore, the null space of T equals 0. Therefore, T is injective, and so T is invertible, right? We showed injectivity and surjectivity, so it is invertible. And therefore, we have shown that C implies A, which completes the proof. Right, so we showed, well, this one, free. We showed this, B implies C, and then C implies A. That's neat. So with operators, again, all of them are these properties, invertibility, injectivity, and surjectivity are equivalent. Now, what's the power of this result? So to show the power of this result, we're going to see an example. So we should show that for each polynomial, Q being a polynomial, there exists a polynomial P with the following property. If we multiply P, the polynomial P, times this trinomial here, x squared plus 5x plus 7, and then take its second derivative, we get Q. So how do we show this? This can be shown, So this example is a lot easier to show with linear algebra, and especially with this theorem, using this theorem. So let's look over our solution. How do we do this? So we're gonna restrict our attention to the polynomials with degree m, right? Because these vector spaces are infinite dimensional, right? So we're restricting it to finite dimensional. So suppose Q is a polynomial with highest degree m, or degree less than or equal to m, right? Because polynomials can't be, we can't have infinite degree. And we're going to define this polynomial, the mapping T, to map the polynomial P by multiplying again by this trinomial and then taking the second derivative. Well, how do we know T is an operator? So again, the question is, how do we know that T is indeed an operator? If you want to think about it, go ahead and pause. But the reason we know it's an operator is because multiplying times that trinomial increases the degree by 2. But then taking the derivative twice reduces the degree by 2. That's how we know T is an operator, right? It's mapping to its space, the same space. So every polynomial whose second derivative equals 0 is of the form ax plus b, where a and b are real numbers, right? So even if we get the a constant polynomial p and we multiply it by this trinomial, we're not going to get something of this form. So the null space of T is 0. The only way we're going to get that our second derivative is 0 is if P is 0. So null space of T is 0. Therefore, T is injective. And what does our theorem tell us? That T is therefore surjective as well. Therefore, there exists a polynomial P such that P times this trinomial and then taking the derivative twice equals Q, the polynomial Q, as desired. So it's pretty neat what this theorem can do. So in the next section, again, like I said, operators are going to keep coming back. But next section, we're going to be looking at products and quotients of vector spaces.